Hello, everybody. Welcome in. Hope you're having a good day today. Let me go ahead and get things set up here. Hello, everybody. Okay. All right. Anybody here? Hello? Hello? Anybody there? I don't know one. That's crazy. All right. Hello, everybody. Welcome. Hope you're having a good day today. Today marks a interesting day. Should be a fun one. Yeah, it should be a fun time. Um, I'm gonna record this, I think, and yeah, I think we're gonna record this and make it a series on the channel. It might have a lot of interest. What the heck happened to my screen here? There we go. It was just cut off. All right, everybody. Hope you're having a good day today. I'm gonna take out the old shoes here. Let the feet breathe. You stand up here, let my legs get some blood flow. Been sitting all day, right? At work, back in the desk. Anywho, we're gonna get into this one today. This is gonna be the start of a long journey. You know, they always say, you can't learn anything unless you start, and you do, so that's what we do. So anyways, I appreciate you being here and hanging out with me today. Today's going to be fun as we are going to dive into machine learning and deep learning in Python specifically. That's kind of like the standard language typically with these types of things. So good thing we already know Python. We don't have to go through like a Python course before with this and then try to learn machine learning on top of that. So hopefully we can, be able to, focus on the machine learning part and not so much the Python part, as we've already learned Python. Okay, I'm gonna go ahead and record the video, and we'll get into it today. All right. Hello, everybody. Thanks so much for joining me. Welcome back to the channel. Hope you're having a wonderful day so far. My name is Michael. Today we're going to be jumping back. Oh, no. Today we're going to be starting something new. We're going to be jumping into some deep learning with Python. Today marks episode 1 of 25, day 1 of 25 of learning machine learning with Python. So we're going to be starting off with this material. Reading through this would be nice, getting some, whatever. If you want to, whatever, I'll just chop it up later. If you want to follow me live on the stream where I read this live, I do it almost every single day. Teach myself computer science and programming from the ground up in Python, C, front end, back end, you name it. Thanks so much for being here. Let's get started. Okay. Well, nowhere to go but in, right? Here we go. Hope you're having a good day, you guys. Welcome in. This should be a fun one. Chapter 1, what is deep learning? This chapter covers high-level definitions of fundamental concepts, a soft introduction to principles behind machine learning, deep learning's rising popularity and future potential. Over the past decade, artificial intelligence, AI, has been a subject of intense media hype. Machine learning, deep learning, and AI have come up in countless articles, often outside of technology-minded publications. We're promised a future of intelligent chatbots, self-driving cars, and virtual assistants, a future sometimes painted in a grim light, and other times as utopian. A future sometimes painted in a grim light and other times as utopian, where human jobs will be scarce and most economic activity will be handled by robots or AI agents. For a practitioner of machine learning, it's important to be able to recognize the signal amid the noise, so that you can tell world-changing developments from overhyped press releases. Our future is at stake, and it's one in which you have an active role to play. After reading this book, you'll be one of those who can develop these AI systems. Let's tackle these questions. What has deep learning achieved so far? How significant is it? Where are we headed next? Should you believe the hype? All right. Here we go. We're really going to focus on notes. All right. Artificial intelligence, machine learning, and deep learning. First, we need to define clearly what we're talking about when we mention AI. What are artificial intelligence, machine learning, and deep learning? How do they relate to each other? We have a graph here with deep learning nested in between machine learning and then artificial intelligence overall. Artificial intelligence was born in the 1950s when a handful of pioneers from the nascent fields of computer science started asking whether computers could be able to think, a question whose ramifications we're still exploring today. While many of the underlying ideas have been brewing in the years, and even decades prior, artificial intelligence finally crystallized as a field of research in 1956 when John McCarthy, then a young assistant professor of mathematics at Dartmouth College, organized a summer workshop under the following proposal. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machine use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. At the end of the summer, the workshop concluded without having fully solved the riddle. It set out to investigate. Nevertheless, it was attended by many people who would move on to become pioneers in the field, and it set in motion an intellectual revolution that is still going on to this day. Concisely, AI can be described as the effort to automate intellectual tasks normally performed by humans, such as AI is a general field that encompasses machine learning and deep learning, but that also includes many more approaches that may not involve any learning. Consider that until the 1980s, most AI textbooks didn't mention learning at all. Early chess programs, for instance, only involved hard coded rules crafted by programmers and didn't qualify as machine learning. In fact, for a fairly long time, most experts believed that human level artificial intelligence could be achieved by having programmers handcraft a sufficiently large set of explicit rules for manipulating knowledge stored in explicit databases. This approach is known as symbolic AI. It was the dominant paradigm in AI from the 1950s to the late 1980s, and it reached its peak popularity during the expert systems boom in the 1980s. Although symbolic AI proved suitable to solve well defined logical problems such as playing chess, it turned out to be intractable to figure out how explicit rules for solving more complex, fuzzy problems such as image classification, speech recognition, or natural language translation. A new approach arose to take symbolic AI's place: machine learning. Okay, let's take some notes here. So, AI can be described as the effort to automate intellectual tasks normally performed by humans. Right? Okay, cool. So then we have this thing called symbolic AI. Right, symbolic AI is for a fairly long time, most experts believe that human-level artificial intelligence can be achieved by having programmers handcraft a sufficiently large set of explicit rules for manipulating knowledge stored in an explicit database. So, sufficiently large set of explicit rules. Set of explicit rules for manipulating knowledge stored in explicit databases, right? Kind of like faking it almost, just with so many parameters of custom, edge cases that it kind of feels artificial intelligent, right? All right. Hey Panda, how's it going? Hey Vizzy, hey Vontrell, what's going on, you guys? Okay. Machine learning. In Victorian England, Lady Ada Lovelace was a friend and a collaborator of Charles Babbage, the inventor of the analytical engine, the first known general-purpose mechanical computer. Although visionary and far ahead of his time, the analytical engine wasn't meant as a general-purpose computer when it was designed in the 1830s. Although visionary and far ahead of his time, the analytical engine wasn't meant as a general-purpose computer when it was designed in the 1830s and 1840s. Because of the concept of general-purpose computation was yet to be invented. It was merely meant as a way to use mechanical operations to automate certain computations from the field of mathematical analysis, hence the name analytical engine. As such, it was the intellectual descendant of earlier attempts at encoding mathematical operations in gear form, such as the Pascaline, Pascaline and Leibniz step-Rochner, a refined version of the Pascaline designed by Blaise Pascal in 1642 at age 19. The Pascaline was the world's first mechanical calculator. It could add, subtract, multiply, or even divide digits. In 1843, Ada Lovelace remarked on the invention of the analytical engine. The analytical engine has no pretensions whatsoever to originate anything. It can do whatever we know how to order. What is this way of writing? The analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. Its province is to assist us in making available what we're already acquainted with. Even with 182 years of historical perspective, Lady Lovelace's observation remained arresting. Could a general purpose computer originate anything? Or would it always be bound to dully executed processes we humans fully understand? Could it ever be capable of any original thought? Could it learn from experience? Could it show creativity? Her remark was later quoted by AI pioneer Alan Turing as Lady Lovelace's objection in his landmark 1950 paper Computing Machinery and Intelligence, which introduced the Turing test as well as key concepts that would come to shape AI. Turing was one of the opinion highly provocative at the time that computers could in principle be made to emulate all aspects of human intelligence. The usual way to make a computer do useful work is to have a human programmer write down rules. A computer program to be followed to turn input data into appropriate answers, just like Lady Lovelace's writing down step-by-step instructions for the analytical engine to perform. Machine learning turns this around. The machine looks at the input data and the corresponding answers and figures out what the rules should be. So this takes in rules and data into classical programming and provides answers, whereas data and answers are provided into machine learning to provide out rules. A machine learning system is trained rather than explicitly programmed. It's presented with examples relevant to a task, and it finds statistical structure in these examples that eventually allows the system to come up with rules for automating the task. For instance, if you wish to automate the task of tagging your vacation pictures, you could present a machine learning system with many examples of pictures already tagged by humans, and the system would learn statistical rules for associating specific pictures to specific tags like landscape or food. Although machine learning only started to flourish in the 1990s, it has quickly become the most popular and most successful subfield of AI, a trend driven by the availability of faster hardware and larger datasets. Machine learning is related to mathematical statistics, but it differs from statistics in several important ways. In the same sense that medicine is related to chemistry but cannot be reduced to chemistry, as medicine deals with its own distinct systems with their own distinct properties. Unlike statistics, machine learning tends to deal with large, complex datasets, such as a dataset of millions of images, each consisting of tens of thousands of pixels, for which classical statistical analysis, such as Bayesian analysis, would be impractical. As a result, machine learning, and especially deep learning, exhibits comparatively little mathematical theory, maybe too little, and is fundamentally an engineering discipline. Unlike theoretical physics or mathematics, machine learning is a very hands-on field driven by empirical findings and deeply reliant on the advances in software and hardware. Okay, cool. Um, Intelligence. machine, so we'll say machine learning, right? This takes the machine looks at input data and the core answers and figures out what rules should be. So we'll kind of take this photo here. Okay. Learning rules and representations from data. All right. To define deep learning and understand the difference between deep learning and other machine learning approaches, we first need some idea of what machine learning algorithms do. We just stated that machine learning discovers rules to execute a data processing task, given examples of what we'd expect. So to do machine learning, we need three things. Input data points, for instance, if the task is speed recognition, the data points could be sound files of people speaking. Input data points, for instance, if the task is speech recognition, these data points could be sound files of people speaking. If the task is image tagging, they could be pictures. Examples of the expected output in a speech recognition task, these could be human-generated transcripts of sound files. In an image task, example outputs could be tags such as dog, cat, and so on. A way to measure whether the algorithm is doing a good job. This is necessary to determine the distance between the algorithm's current output and its expected output. The measure is used as a feedback signal to adjust the way the algorithm works. This adjustment step is what we call learning. Okay, so learning, right? So, three things in machine learning. Number one is input data points. Number two is examples of the expected output. Number three is a way to measure whether the algorithm is doing a good job. Right? So learning, right? This is necessary to determine the distance between the current output and expected output. The measurement between the machine learning algorithm current output and the expected output. The measure is used as a feedback signal. Used as a feedback signal to adjust the way the algorithm works. Cool. A machine learning model transforms its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs. Therefore, the central problem in machine learning and deep learning is to meaningful transform data, in other words, to learn useful representations of the input data at hand, representations that get us closer to the expected output. Before we go any further, what's a representation? At its core, it's a different way to look at data to represent or encode data. For instance, a color image can be encoded in the RGB format or in the HSV format. These are two different representations of the same data. Some tasks that may be difficult with one representation can become easy with another. For example, the task, quote, select all red pixels in the image is simpler in the RGB format, whereas make the image less saturated is simpler in the HSV format. Machine learning models are all about finding appropriate representations for their input data, transformations of the data that make it more amenable to the task at hand. Let's make it concrete. Sorry, people are being noisy. Okay, so we have representations of data. So we have the central problem of machine learning, right? Is to meaningfully transform data, to learn useful representations of the input data at hand. Right? These are representations that get us closer to the expected output. So then we have representations, right? Then what are representations? Well, representations are kind of any way that you can view data from certain perspectives, right? Certain scientists might view a data set as, or doctors might view certain data sets as different diagnoses, but with given the same data set. That might be not necessarily a representation, actually, because you get the same result whether or not it's the representation used based on this example, right? You have the same image, whether you use RGB or HSV format. You can just use a different representation to manipulate things about the image, whereas the output is consistent. So, it's a different way to look at data to represent or encode data. Right? For example, would be encoding an image in RGB or HSV format. These are different representations of the same image, the same data. All right. Hey, got that right, Starship? Thank you, boy. Appreciate you. Okay. Let's make this concrete. Consider an XY axis and some points represented by their coordinates in the XY system as as shown in figure 1.3. Gosh, I suck at reading, you guys. My stomach hurts though. Okay, here we go. Let's make this concrete. Consider an XY axis and some points represented by their coordinates in the XY system as shown in figure 1.3. As you can see, we have a few white points and a few black points. Let's say we want to develop an algorithm that can take a point's XY coordinate and output whether that point is exactly black or white. In this case, the inputs are the coordinates of our points, and the expected outputs are the colors of our points. A way to measure whether our algorithm is doing a good job could be, for instance, the percentage of points that are being correctly classified. And what we need here is a new representation of our data that cleanly separates the white points from the black points. One transformation we could use, among many other possibilities, would be a coordinate change illustrated in figure 1.4, right? Where we section off using, lines, the various sections, and then kind of translate that into a proper plane. That is just a 90-degree angle created off those points. So if you rotate it, you get just a translation of the coordinate plane, right? In this new coordinate system, the coordinates of our points can be said to be a new representation of our data, and it's a good one. With this representation, the black/white classification problems can be expressed as a simple rule. Black points are such that x is greater than 0, or white points are such that x is less than 0. In this new representation, combined with this simple rule, neatly solves the classification problem. In this case, we define the coordinate changed by hand. We use our human intelligence to come up with our own appropriate representation of the data. This is fine for such an extremely simple problem, but could you do this same task if the task were to classify images of handwritten digits? Could you write down explicitly computer executable image transformations that would illuminate the difference between a 6 and an 8, between a 1 and a 7, across all different handwritings? This is possible to an extent. Rules based on representations of digits, such as counting the number of enclosed loops or vertical or horizontal picture histograms, can do a decent job at telling apart handwritten digits, but finding such useful representations by hand is hard work, and as you can imagine, the resulting rule-based system would be brittle and a nightmare to maintain. Every time you would come across a new example of handwriting that would break your carefully thought out rules, you would have to add new data transformations and new rules while taking into account their interactions with every previous rule. You're probably thinking, if this process is so painful, could we automate it? What if we tried systematically searching for different sets of automatically generated representations of the data and rules based on them, identifying good ones using the percentage of digits being correctly classified in some development datasets as feedback? We would then be doing machine learning. Learning in the context of machine learning describes an automatic search process for data transformations that produce useful representations of some data, guided by some feedback signal, representations that are amendable to simpler rules solving the task at hand. These transformations can be coordinate changes like in our 2D coordinate classification example, or a histogram of pixels and counting loops like in our digit classification example, but they could also be linear projections, translations, and nonlinear operations such as select all points such that x is greater than 0, and so on. Machine learning algorithms aren't usually creative in finding these transformations. They're merely searching through a predefined set of operations called a hypothesis space. For instance, the space of all possible coordinate changes would be our hypothesis space in the 2D coordinates classification example. So that's what machine learning is, concisely searching for useful representations and rules over some input data with a predefined space of possibilities using guidance from a feedback signal. This simple idea allows us to solve a remarkably broad range of intellectual tasks, from autonomous driving to natural language question answering. Now that you understand what we mean by learning, let's look at what makes deep learning special. That was a lot, right? But that was pretty informative. So, right, we have these things like coordinate translations or coordinate change, which can be used, for like a simple rule for, moving or reclassifying data on like a graph per se, or you can do pixel histograms with loop, detections or whatever for classifying handwritten digits. But all of these require like intense rules that, if introducing new data, would require new rules to be implemented by the programmer. So we're trying to figure out ways to automate it via some data set feedback. So these transformations are examples and linear projections and so on. These transformations can be coordinate changes. Right, yeah. Okay. The quote deep in deep learning. Hey Braden, how's it going, dude? Deep learning is a specific subfield of machine learning. It's a new take on learning representations from data, which emphasizes learning successive layers of increasingly meaningful representations. The deep in deep learning isn't a reference to any kind of deeper understanding achieved by the approach. Rather, it stands for this idea of successive layers of representations. How many layers contribute to a model of the data is called the depth of the model. Other appropriate names for the field could have been layered representation learning or hierarchical representations learning. Modern deep learning often involves tens or even hundreds of successive layers of representations, and they're all learned automatically from exposure to training data. Meanwhile, other approaches to machine learning tend to focus on learning only one or two layers of representations of the data, say, taking a pixel histogram and then applying a classification rule. Hence, they're sometimes called shallow learning. In deep learning, these layered representations are learned via models called neural networks, structured in literal layers stacked on top of one another. The term neural network is a reference to neurobiology, but although some of the central concepts in deep learning were developed in part by drawing inspiration from our understanding of the brain, in particular the visual cortex, deep learning models are not models of the brain. There's no evidence that the brain implements anything like the learning mechanism used in modern deep learning models. You may come across pop science articles proclaiming that deep learning works like the brain or is modeled after the brain, but that isn't the case. It would be confusing and counterproductive for newcomers to the field to think of deep learning as being in any way related to neurobiology. You don't need that shroud of just like our mind's mystique and mystery that you may as well forget anything you may have read about hypothetical links between deep learning and biology. For our purpose, deep learning is a mathematical framework for learning representations from data. Why do the representations learned by a deep learning algorithm what okay, sorry. What do the representations learned by a deep learning algorithm look like? Let's examine how a neural sorry. What do the representations learned by a deep learning algorithm look like? Let's examine how a network several layers deep, see figure 1.5, transforms an image of a digit to recognize what digit it is. So the original input is some kind of blurry, 4, and is able to pass through these layers to output out 4. As you can see from this figure, in 1.6 here, where it has different layer representations, and it gets to a guess of about a 4. As you can see in figure 1.6, the network transformations Oh my gosh, I cannot read today. As you can see in figure 1.6, the network transforms the digit image into representations that are increasingly different from the original image and increasingly informative about the final result. You can think of deep network as a multi-stage information distillation process where information goes through successive filters and comes out increasingly purified. That is, useful with regard to some task. So that's what deep learning is. Technically, a multi-stage way to learn data representations. It's a simple idea, but as it turns out, very simple mechanisms, sufficiently scaled, can end up looking like magic. Understanding how deep learning works. Okay, let's go back and get some notes on these guys. So we talked about the depth of deep learning. Deep learning is a specific subfield of machine learning. It's a new take on learning representation from data, which emphasizes learning from successive layers. Okay. A new take on learning representations, which emphasizes learning successive layers of increasing. A new take on data learning representations. Okay. A new take on learning representations. Learning representations from data, which emphasizes learning successive layers of increasingly meaningful representations. A new take on learning representations from data, which emphasizes learning successive layers of increasingly meaningful representations. Deeper understanding, rather, it stands for the idea of successive layers, right? That deep corresponds to the successive layers of representations, right? Where we have depth is just how many layers contribute to the model, right? Which is like how many of the data, right? Nice. So then it talks about how it has relation to biology through the way it got through like neurons in the brain, but it doesn't really have any relation to actually how humans think. It's kind of more of a analytical interpretation used as like a guideline almost, kind of what it was describing. So we could like describe, we have these things called neural networks, right, which we've heard of before. It talks about how deep learning, the layers representation are learned via models called neural networks. Structured in literal layers stacked on top of each other. So these are layered representation models. Right, layered representation models. Um, the term neural reference from neurobiology, blah, blah, blah. Deep learning models are not models of the brain. There's no evidence of that. Maybe come across pop science articles proclaiming is what makes the brain work, but it isn't the case, blah, blah, blah. Right, and then it talks about here, the network transforms digit image into representations that are increasingly different from the original image, increasingly informative in the final result. So we'll kind of paste the image here that we got, and then also kind of this one here. Right, so it kind of is doing this information distillation process where it's trying to filter out the image or information data given to come to some sort of more cleanly final result, based on some sort of feedback loop parameters within. So it talks about how you have the network transforms. So in the example, the network transforms the digit image into representations that are increasingly different from the original image and increasingly more informative about the final result. So it has this kind of concept of a multi-stage information distill process, where information goes through successive filters and comes out increasingly how do you do, I forgot, it's how do you do, I forgot how to do it's not italic tags, is it? It's, oh, yeah, that's right. Okay. Cool. Understanding how deep learning works in these three figures. At this point, you know what machine learning is about: mapping inputs, such as images, to targets, such as the label cat, which is done by observing many examples of inputs and targets. You also know that deep neural networks do this input to target mapping via a deep sequence of simple data transformations, layers, and that these data transformations are learned by exposures to examples. Now let's look at how this learning happens concretely. The specification of what a layer does to its input data is stored in the layer's weights, in which, in essence, are a bunch of numbers. In technical terms, we'd say that the transformation implemented by a layer is parameterized by its weights. See figure 1.7. Weights are also sometimes called the parameters of a layer. In this context, learning means finding a set of values for the weights of all layers in a network such that the network will correctly map example inputs to their associated targets. But here's the thing. A deep neural network can contain tens of millions of parameters. Finding the correct value for all of them may seem like a daunting task, especially given that modifying the value of one parameter will affect the behavior of all others. Okay, interesting. So parameterized by its weights. In this context, machine learning finds a set of values for the weights of all layers in the network such that the network will correctly map inputs to associated targets. So kind of balancing out weights. So the goal, finding the right values for these weights. We have some weights that are given in at each layer. We have our input layer and our prediction. To control something, first you need to be able to observe it. To control the output of a neural network, you need to be able to measure how far this output is from what you expect. This is the job of the loss function of the network, also sometimes called the objective function or cost function. The loss function takes the prediction of the network and the true target, what you want the network to output, and computes the distance score, capturing how well the network has done on the specific example. Interesting. Okay, so a lot going on here. So the control of the output is a neural network. You need to be able to measure how far the output is from what you expect. This is the job of the loss function. The loss function takes the predictions of the network and the true target, what you wanted the network to output, and computes a distance score. Okay, so we have a prediction and our true target, we feed it to a loss function, and we have a loss score here. And does that then re-feed back into here to kind of keep going? Let's see. The fundamental trick in deep learning is to use this score as a feedback signal to adjust the value of the weights as little. Oh my gosh, I suck at reading today. The fundamental trick in deep learning is to use this score as a feedback signal to adjust the value of the weights a little, in a direction that will lower the score for the current example. This adjustment is the job of the parameter. Oh my gosh, dude! That dog needs to shut up. No one wants to hear that dog barking all day. Can you guys hear that dog? Kind of. It's probably annoying. I don't want to be back on the recording. Okay. Here we go. That dog is really loud though. Barely. I'm gonna yell and say like, "Yo, shut that dog up." Nah, you can't hear the dog? Okay. Let me know if it's annoying. I'll yell. Why that damn dog? Okay. The fundamental trick dude, what is wrong with me? The fundamental trick in deep learning is to use this score as a feedback signal to adjust the value of the weights a little, in a direction that will lower the loss score for the current example. This adjustment is the job of the optimizer, which implements what's called the backpropagation algorithm, the central algorithm in deep learning. The next chapter explains in more detail how backpropagation works. Okay, so you have X input data, goes through some layers of data transformation in which apply weights at each layer. These weights, fine-tune each adjustment layer corresponding to which, however the layer, does this distillation of the input data to result in some output prediction Y. We take the output prediction Y and a true target value we're expecting and compute some sort of loss function. This is basically like some score about how well, our machine learning deep learning performed. We then have a loss score, which is fed to an optimizer, which readjusts the weights. And we have this feedback loop that happens to adjust these weights to get a loss score as minimized as possible, which means our predictions will hopefully be accurate, right? That makes sense. Dude, that dog, though, it's distracting me. It might not be distracting you guys, but for me, trying to learn about deep learning with a dog barking in your ear is kind of it's not going to work. Okay, so let's take some notes here on understanding how deep learning works. Okay. In 3 figures. understanding how deep learning works in 3 figures. Right, so blah, 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 blah. Let's look at the learning happens, layer input data. Okay, so we have weights, right? And we know that weights are parameterized, factors, parameter factors applied at each, network layer that slightly that don't go. Oh, hold on. I'll come back later. Parameter factors applied at each network layer that adjust the output slightly. That adjust the output. Something like that. So let's then solidify the definition here. Store the specification of what a layer does. So like we'll say the specification of what a layer does to its input data. Right? This is just like applying a weighted function to like, certain data that have more prevalence in like we've used kind of this terminology or this kind of thinking in biology in college. I've done this in chemistry, finding weighted concentrations of solutions, things like this where you have more concentration for a certain molarity of a solution in it combined, and trying to find purity values. What is going on? This is just frustrating me. Get out of here. Get out of here, Cord. Get out of here. Go. Go. Get out of here. Go. Jeez. Okay. So, we say that the transformations implemented later are parameterized by the weights. Transformations implemented by a layer are parameterized by its weights. In this context, learning means finding a set of values for the weights. So we'll kind of make a note here and say, in this context, learning means finding a set of values for the weights of all layers in a network such that the network will correctly map example inputs to their associated targets. We need to be able to observe it. Right here we go. Gotcha. Okay, so we have a loss function, also known as the objective function, yeah, or cost function. So this is so the loss function is a function given the outputted value of the network and the true expected values, a function that produces a loss score when a function when given the output prediction of the network and the expected true results, a function when given the output prediction of the network and the expected true results computes a, quote, loss score. Right, a loss score is a value determining the success, a value computed by the loss function that determines the success of the output of the network when compared to the expected results. So this value, so we'll say it says lower value, lower the loss score, better the results. Our goal is to obtain a loss score that is as low as possible, right? Or like, as close, which means as close to the expected result, right? So we want to feed this loss score. So a loss score this score is a feedback signal to adjust the value of the weights a little in a direction that will lower the loss score. So then we have the loss score is fed into an optimizer, which will update the weight values at each layer of the network. Boom. So we have an optimizer, right, which we know is a function that when given a loss score will adjust the weights at each network layer if needed to hopefully produce a lower loss score closer to the expected results. Beautiful. Hey Zen, what's going on, boy? This will be a good time to step in here and learn with us here. Cool. So we've learned about loss scores, the loss function that computes the loss score given predictions and the actual targets, weights at each layer, right? This is kind of review from neural network stuff. Okay, so which implements what's called back propagation. So this is what's called back propagation algorithm. The central algorithm in deep learning. Cool. Nice. So let's go ahead and grab this boy. Well, we don't need, actually, we just need the one example because it's all the same. Because it has this with a full on it. Right, boom. Okay. Did I read this? I don't think so. Initially, the weights of the network are assigned random values, so the network merely implements a series of random transformations. Naturally, its output is far from what it should ideally be, and the loss score is accordingly very high. But with every example the network processes, the weights are adjusted a little in the correct direction, and the loss score decreases. This is the training loop, which repeated a sufficient number of times, typically tens of passes over thousands of examples, yields weight values that minimize the loss function. A network with a minimal loss is one for which the outputs are as close as they can be to the targets. A trained network, oh, a trained network. This reading is kind of funky. Once again, it's a simple mechanism that, once scaled, ends up looking like magic. Cool. So far, so good. I'm feeling really confident so far about this. That's the, I'll eat crow in a second, right, when we get into the future chapters, but understanding everything pretty good so far. But I'm sure it's going to get really hard soon. Feeling good, though. We're confident, we're optimistic, and we're happy. What field of software are you engineering for? I'm not in. I'm just a chemist, biochemist. How's it going, dude? Trying to learn for fun. After a while, I was searching for YouTube for someone who streams about learning deep learning. I couldn't find anyone, so I gave up. Then, out of nowhere, YouTube recommended me. Boom! Here we go. Welcome in, dude. Hey, Jamal. Yeah, this is day one. We're starting this 25 days of machine learning, or whatever. How many chapters are this? There's like 20 or so, but I think I put 25 on accident. This is deep learning with Python. I'll post a link of the book in my Discord down below. I'll make a section of it after the stream today. And I'm also recording this for re-upload for condensed version to the channel. Okay. What makes deep learning different? What makes deep learning different? Is there anything special about deep neural networks that makes them the, quote, right approach for companies to invest in and for researchers to flock to? Will we still be using deep neural networks in 20 years? Deep learning has several properties that justify its status as an AI revolution, and it's here to stay. We may not be using neural networks many decades from now, but whatever we use will directly inherit from modern deep learning and its core concepts. These important properties can be broadly sorted into three categories. Simplicity. Deep learning makes problem solving much easier because it automates what used to be the most crucial step in machine learning workflow. Feature engineering. Previous machine learning techniques, shallow learning, only involved transforming the input data into one or two successive representation spaces, which wasn't expressive enough for most problems. As such, humans had to go to great lengths to make the initial input data more amendable by processing. By these methods, they had to manually engineer good representations for their data. This is called feature engineering. Deep learning, on the other hand, completely automates this step. With deep learning, you learn all features in one pass rather than having to engineer them yourself. This has greatly simplified machine learning workflows often replacing sophisticated multi-stage pipelines with a single simple end-to-end deep learning model. Interesting, right? So because you have the backpropagation feedback loop of deep learning, you have like automatic feature engineering that's taken place rather than having to maybe interject at each step potentially. Scalability. Deep learning is highly amenable to parallelization on GPUs or more specialized machine learning hardware, so it can take full advantage of Moore's law. In addition, deep learning models are trained by iterating over small batches of data, allowing them to be trained on datasets of arbitrary size. The only bottleneck is the amount of parallel computational power available, which, thanks to Moore's law, is a fast-moving barrier. And versatility and reusability. Unlike many prior machine learning approaches, deep learning models can be trained on additional data without restarting from scratch, making them viable for continuous online learning, an important property for very large production models. Furthermore, trained deep learning models are repurposable and thus reusable. This is the big idea behind foundation models. Large models trained on homogeneous amounts of humongous amounts of data. Large models train on humongous amounts of data, which can be used across many new tasks with little retraining or even none at all. Okay. So we have simplicity, right? Deep learning because it automates what used to be the most crucial step in machine learning workflow, the feature engineering. So this automates what we call feature engineering, right? Previous machine learning techniques, shallow learning, only involved transforming the input data into one or two successive representation spaces, which wasn't expressive enough for most problems. As such, humans had to go to great lengths to make initial input data more amenable to processing these methods. They had to manually engineer good representations for the data. This is called feature engineering, right? Because deep learning, I guess, starts at random. Is that kind of where it's getting at? So if we kind of say like, let's first say like feature engineering. Let's define feature engineering. So this is like tailoring your input data to get like humans had to go to great lengths to make the initial input data more amenable by processing by these methods. They had to manually engineer good representations for their data. This is called feature engineering. Making them more, okay, so here. Making the initial input data more amenable by processing by these methods. Feature engineering. Let's ask. Let's get some definition here. Can you define feature engineering for me in simple terms in relation to machine learning? Feature engineering is the process of turning raw data into better inputs for machine learning model. A model is only as good as what you feed it. Raw data is often messy. Feature engineering, you have to just clean up and reshape it. So this is why deep learning is, considered more simple over these steps, is because you take in random data you take in random weights, right? And the weights are then adjusted to then the data. So how does that differ then? it moves it inside the model, right? Neural networks start off with random weights. Those weights get adjusted based on the data. That's true for almost all machine learning models, not just deep learning. The real difference isn't randomness, it's who is responsible for creating useful features. Traditional machine learning, what you described earlier, is manually creating features, describes what matters, learns how to weight those features. You do a lot of the thinking up front. You feed more raw, minimal processed data and learns what the features matter and how to use them. Mm. Interesting. So, manually tailoring the input data to receive better results depending on, or so like kind of. Whereas simplicity, in standard or in deep learning, this process is moved internally inside the system rather than human interjection. Something like that. Features, characteristics ascribed to the data. Okay. So, simplicity, deep learning makes problem solving much easier, automates what's usually the critical step, is feature engineering. Deep learning, on the other hand, completely automates this step. With deep learning, you learn all the features in one pass rather than having to engineer them yourself. Yeah, that makes sense. Right, we have those feedback loops. So scalability is deep learning is highly amendable. Well, it wouldn't. Now, I guess we'll learn how the data input differs from being messed with manually or something, Not, yeah. Choosing those characteristics then tell your model to extract a pattern from it. Yeah, I would do the Python Crash Course book if you're looking to get into Python. Um, and doing Harvard CF50P at the same time. Hey Tim, how's it going, dude? I'm also doing that. I can really see an improvement in memory understanding. I mean, yeah, it's kind of just taking notes. It's a pretty common thing. You got it, Gustav. Feature engineering would be like adding a feature for the number of loops and the number of straight lines. Oh, got you. So that's a good callback, Braden, right? So if you remember back at the beginning of the chapter, it talked about how um, for brute kind of more brute force, what was it called? What was the term? It was a term. Symbolic AI, right? Where we had sufficiently large explicit rules that kind of made it seem like it was artificial, but it was just so many parameters that were defined by human that for like chess AI or whatever, right? In this certain situation, play this move or like do these like moves, right? So, um, so Braden's saying feature engineering would be like adding features for the number of loop detection or straight lines on the image handwritten digits. Yeah. Backpropagation uses derivatives in the chain rule. Gotcha. Okay, cool. Good discussion, y'all. Good discussions. I like that. I like that. We're all on the same page. We're all good? Okay. Um, if you guys are here, I'll quickly do a quick plug while we have some new people here. We released a new project and we built a full stack app live on stream here. If you guys haven't visited our site yet, polyworld.app. Go check it out. Um, that guy I showed, that that guy, he actually lost his streak today. I've been keeping up on him. He lost his streak, so he's gone. He didn't get picked up by the board, so he lost his streak. But so this is the max appearance guy. He's down pretty big on a, but he has a huge balance. So, but he's down he's down pretty large. So he might be waiting for some things to turn around. But if you guys haven't checked out our prediction market leaderboard, make sure you go check it out. You can also do your own better searches if you make an account, and search up any address you would like for up to 30 days in the past. So yeah, and make a snapshot. So go ahead and check out Polyworld, our full stack app, if you haven't yet. Shameless plug. I'll go ahead and put a pin chat. Okay. Okay, so feature engineering, right? Deep learning, on the other hand, end-to-end model. Scalability, deep learning is highly amendable to parallelization on GPUs, more specialized machine learning hardware. So we don't really have a lot of experience with GPUs at all, so this is a little bit abstract for us. It's highly amendable to parallelization on GPUs, more specialized hardware. Kind of just copy that. Right. So it can take full advantage of Moore's law. So let's define this. I've never heard of this law, but maybe I have, but I'm not sure. Moore's, I just can't remember, law. All right, let's look it up. Who's got Moore's law in here off the top of their head? Moore's law is the observation that the number of transistors on an integrated circuit tends to double roughly every 2 years, leading to steady increases in computing power and decreases in cost per transistor. What it means is more transistors, more processing capability in the same physical space. Now, are we going to have a bottleneck soon with how low we can go? Now that we're getting into smaller nanometers or whatever, are we having some bottlenecks on how many transistors we can start to fit into space? I mean, we could go down to like what, the electron level? The short answer is yes, you're hitting a real bottleneck. It's not an engineering problem, it's a physics problem. The 3 nanometer or 2 nanometer nodes you're dealing with stretch only a few dozen silicon atoms wide. I mean, yeah, you're going to have to start turning on and off like electrons or something, which I don't think you're going to be able to do. So what's the next thing, like turning on and off electrons? Protons or something? They already are turning them off in the transistor right now. Oh, that's right. You have to go like, I mean, you can't go smaller than some, you have a couple silicon atoms wide, but you can go down to the singular atom level, which would be like what? Qubits? Quantum computing at the atom level? Photonic computing? What the hell? Oh, here it is. Photonic computing. Right now, it's the most used data transfers, fiber optics, not CPUs. Oh. So rather than being limited to physical, you just do light based. Wow, interesting. So rather than being physical, you would just being photonic be like light based and have, you know, but then how would you would have to have sensors for, I mean, you could do like how currently you have like wells or whatever on the silicon plates, like microscopic wells that I guess could detect the light source, but then you're still limited to physical spaces. You think about this the right way, and you're also spotted the catch. Light still lives in the physical world. You can't magically escape space limits. Photons replace electrons one to one. The The photonic has no physical constraints. Light is a wavelength. You can't confine light structure smaller than half its wavelength to its exotic tricks. Now we're getting into some crazy stuff. Yeah, gotta get into some crazy stuff. Okay, so Moore's law is the idea that the number of available transistors will double every how many years? Double roughly every 2 years. Um, right. Okay. So then we can say learning, so I could take it so it can take full advantage of Moore's law. In addition, deep learning models are trained by iterating over small batches of data, allowing them to be trained on data sets of arbitrary size. Versatility and reusability. Unlike many prior machine learning approaches, deep learning models can be trained on additional data without starting from scratch. That's right. So versatility and reusability. Oh. So unlike many prior deep learning models can be trained on additional data without restarting from scratch, making them viable for continuous online learning. Okay. Okay. Yeah, we're ready to move on. We're almost done with the chapter. The age of generative AI. Yeah, I like to think about a backpropagation is just that it's effectively helping the neural network understand what nodes lead to the desired outcomes. So yeah, not gonna tell you. Thanks, bro. Thanks for coming in. I gotta start chapter 2. You want me to start chapter 2 today? I can't do both in one day. I already worked all day today. Okay, the age of generative AI. Perhaps the most well-known example of deep learning today is the recent wave of generative AI applications. Chatbot assistants like ChatGPT, Gemini, and Claude, as well as image generation, as well as chatbot assistants like ChatGPT, Gemini, and Claude, as well as image generation services like Midjourney. These applications have captured the public imagination with their ability to produce informative or even creative content in response to simple prompts, blurring the lines between human and machine creativity. Generative AI is powered by very large foundation models that learn to reconstruct the text and image content fed into them, reconstruct a sharp image from a noisy version, predict the next word in a sentence, and so on. This means that the targets from figure 1.8 are taken from the input itself. This is referred to as self-supervised learning and enables those models to use vast amounts of unlabeled data, doing away with the manual data annotations that bottlenecked previous brands of machine learning has unlocked a level of scale never seen before. Some of these foundation models have hundreds of billions of parameters, are even trained on over 1 petabyte Ah, some of these foundation models have hundreds of billions of parameters and are trained over 1 petabyte of data at the cost of tens of millions of dollars. These foundation models operate as a kind of fuzzy database of human knowledge, making them amenable to a very wide range of applications without needing special purpose programming or retraining. Because they've already memorized so much, they can solve new problems merely via prompting, querying the knowledge representations they've learned and returning the outputs most likely to be associated with your prompt. Generative AI only rose to mainstream awareness in 2022, but it has a long history. The earliest experiments with text generation date back to the 1990s. The first edition of this book, released in 2017, already had a hefty chapter titled Generative AI that explored the text generation and image generation techniques of the time, while promising them outlandish notion that soon much of the cultural content we consume would be created with the help of AI. So this one's more informative, right? So we have something called generative AI, right? You've obviously heard of this in the media. The generative is powered by very large foundation models. Powered by very large models that learn to reconstruct the text and image content fed into them reconstruct a sharp image from a noisy one, predict the next word in a sentence, etc. So what we'll say is for figure 1.8, true targets here, are given via the data itself. So that's interesting, right? So it says that the targets to hit, the expected targets, right, are taken from the input itself. This is referred to as self-supervised learning. Self-supervised learning. Okay. Cool. That's kind of enough for that one. I've never read this book, but I just did glance over it, and it seems like chapter 2 has some really good visual intuitions along with the math, which will make learning a lot easier. Sweet. We'll have to, I can't wait to get into chapter 2. What do I do for work? I work as a, I just recently changed jobs. It's not as impressive anymore, I guess, but I was a chemist for 4 years. I worked as a chemist and I still work for the same company, but I took a different role, so I could get to a different city, be with my girlfriend, and buy a house and stuff. So I took a role as an equipment manager, equipment lead for the lab here in this area. So I manage like all the equipment on the site and make sure it's all calibrated and maintained, and I do a lot of like more administrative work now, audit preparation work and stuff, more like lab admin management. Okay, Next, almost there. What deep learning has achieved so far? Over the past decade, deep learning has achieved nothing short of a technological revolution, starting with remarkable results on perceptual tasks from 2013 to 2017, then making fast progress on natural language processing tasks from 2017 to 2022, and culminating with a wave of transformative generative AI applications from 2022 to now. Deep learning has enabled major breakthroughs, all in extremely challenging problems that have had long eluded machines. Fluent and highly versatile chatbots such as ChatGPT and Gemini, programming assistants like GitHub Copilot, photorealistic image generation, human-level image classification, human-level... Dude, what is wrong with me? Sorry, you guys. Ugh. Human-level speech transcription, human-level handwriting transcription and printed text. Human-level handwriting transcription and printed text transcription. Dramatically improved machine translation. Dramatically improved text-to-speech conversion. Human-level autonomous driving already deployed to the public in Phoenix, San Francisco, Los Angeles, and Austin as of 2025. Improved recommender systems as used by YouTube, Netflix, or Spotify. Superhuman Go, chess, and poker playing. We are still exploring the full extent of what deep learning can do. We've started applying it with great success to a wide variety of problems that were thought to be impossible to solve just a few days ago. Automatically transcribing the tens of thousands of ancient manuscripts held in the Vatican's secret archive, detecting and classifying plant diseases in fields using a simple smartphone, assisting oncologists or radiologists with interpreting medical imaging data, predicting natural disasters such as floods, hurricanes, and even earthquakes. With every milestone, we're getting closer to an age where deep learning assists us in every activity and every field of human endeavor: science, medicine, manufacturing, energy, transportation, software development, agriculture, and even artistic creation. Cool. Not really any notes in there worth taking, just kind of like more like learning about overall. Beware of the short-term hype. This seemingly unstoppable string of success has led a... I don't know why I'm struggling. This seemingly unstoppable string of success has led to a wave of intense hype, some of which is somewhat grounded, but most of which is just fancy fairy tales. In early 2023, soon after the release of ChatGPT 4 by OpenAI, many pundits were claiming that no one needed to work anymore, and that mass unemployment would be coming within a year, or that economic productivity would soon shoot up by 10x or 100x. Of course, 2 years later, none of this has come to pass. The unemployment rate in the United States remains low, while productivity metrics are far from the promised explosion. Don't misunderstand the impact of AI. In particular, generative AI is already considerable and is growing remarkably fast. As of mid-2025, generative AI was generating tens of billions of dollars in revenue per year, which is extremely impressive for an industry that did not exist 2 years ago. But it doesn't yet make much of a dent in the overall economy and pales in comparison to the absolute unbridled promises we were inundated with at its onset. Some of these words, this writer has some vocabulary to him. Better than mine, that's for sure. While discussions about unemployment and 10x productivity gains triggered by AI are... Dude! What's going on? Ah! Ah! Oh my gosh. Ah. Okay. While discussions about Sorry, you guys. It's been a long day. While discussions about unemployment and 100x productivity gains triggered by AI are already stirring anxieties, there are even more sensational side to AI hype. This side proclaims the imminent arrival of human-level general intelligence, or AGI, or even superintelligence, far surpassing human capabilities. These claims are fueling fears beyond economic disruption. The human species itself might be in danger of being replaced by our digital creators. It might be tempting for those new to the field to assume that it is the practical success of generative AI that caused the belief in near-term AGI, but that is actually backward. The claims of near-term AGI came first, and they significantly contributed to the rise of generative AI. As early as 2013, there were fears among tech elites that AGI might be coming within a few years. Back then, the idea was that DeepMind, a London AI research startup acquired by Google, was on track to achieve it. This belief was the impetus behind the founding of OpenAI in 2015, which initially aimed to be an open source counterweight to DeepMind. OpenAI played a critical role in kickstarting generative AI, so in a peculiar twist, it was the belief in near-term AGI that fueled the ascent of generative AI, not the other way around. In 2016, OpenAI's recruitment pitch was that it would Dude, what is wrong? In 2016, OpenAI's recruiting pitch was that it would achieve AGI by 2020. To be fair, though, only a minority of people in the tech industry believed in such an optimistic timeline back then. By early 2023, however, a significant fraction of engineers in San Francisco Bay Area seemed convinced that AGI would be coming within the following couple of years. It's crucial to approach such claims with a healthy dose of skepticism. It's crucial to approach such claims with a healthy dose of skepticism. Despite its name, today's artificial intelligence is more accurately described as cognitive automation, the encoding and operationalism of human skills in knowledgeable. AI excels at solving problems with narrowly defined requirements or those where ample, precise examples are available. It's about enhancing the capabilities of computers, not about replicating human minds. To be clear, cognitive automation is incredibly useful, but intelligence, cognitive autonomy, is a different creature altogether. Think of it this way: AI is like a cartoon character, while intelligence is a living being. A cartoon, no matter how realistic, can only act out the scenes it was drawn for. A living being, on the other hand, can adapt to the unexpected. If the cartoon is drawn with sufficient realism and covers sufficiently many scenes, what's the difference, you may ask? If a large language model can output a sufficiently human-sounding answer when asked a question, does it matter if it possesses true cognitive autonomy? The key difference is ability. Intelligence is the ability to face the unknown, adapt to it, and learn from it. Automation, even at its best, can only handle situations it's been trained on or programmed for. That's why creating robust automation is so challenging. It requires accounting for every possible scenario. So don't worry about AI suddenly becoming self-aware and taking over humanity. Today's technology simply isn't headed in that direction. Even with significant enhancements, AI will remain a sophisticated tool, not a sentient being. It's like expecting a better clock to lead to time travel. They're just different things altogether. That's comforting to know. Right. All right. Summer can turn to winter. Is this the last section? Almost. Thanks for hanging in there with me, guys. My mouth's getting tired. The danger of inflated short-term expectations is that when technology inevitably falls short, research investment could dry up, slowly progress, slowing progress for a long time. This has happened before, twice in the past. AI went through a cycle of intense optimism followed by disappointment and skepticism, with a dearth of funding as a result. It started with a symbolic AI in 1960s. In those early days, projections about AI were flying high. One of the best-known pioneers and proponents of symbolic AI approach was Minsky, Marvin Minsky, who claimed in 1967, within a generation, the problem of creating artificial intelligence will have substantially been solved. 3 years later, in 1970, he made a more precisely quantified prediction. In from 3 to 8 years, we will have a machine with the general intelligence of a human being. In 2025, such an achievement still appears to be far in the future. So far that we have no way to predict how long it will take, but in the 1960s and early 1970s, several experts believed it to be right around the corner, as do many people today. A few years later, as these high expectations failed to materialize, researchers and government funds turned away from the field, marking the start of the first AI winter, a reference to a nuclear winter because this was shortly after the height of the Cold War. It wouldn't be the last one. In the 1980s, a new take on symbolic AI expert systems started gathering steam among large companies. A few initial success stories triggered a wave of investment, with corporations around the world starting their own in-house AI departments to develop expert systems. Around 1985, companies were spending over $1 billion each year on the technology, but by the early 1990s, these systems had proven expensive to maintain, difficult to scale, and limited in scope, and interest died down. Thus began the second AI winter. We may be currently witnessing the third cycle of AI hype and disappointment, and we're still in the phase of intense optimism. My current view is that we're unlikely to see a full-scale retreat away from AI research like we saw in the 90s. If there is a winter, it should be very mild. AI has already demonstrated its world-changing value. However, it seems inevitable that some air will need to be let out of the 2023-2024 AI bubble. Currently, AI investment primarily in data centers and GPUs surpasses $100 billion annually, while revenue generation lags significantly, closer to $10 billion. AI is currently being judged by executives and investors not by what it has accomplished, but we are told it might soon be able to do, much of which will do. AI is currently being judged by executives and investors not by what it has accomplished, but by what we are told it might soon become able to do, much of which will durably stay out of reach of existing technologies. Something will have to give. But what will happen precisely as the AI bubble deflates is still up in the air. And last section here. Sorry that I have been Mr. Stutter over here, like literally, like Mr. Stutterbug. I don't know what's going on. This guy's writing style is kind of throwing me for a loop. He uses a lot of pauses and like M dashes and stuff, which he kind of writes like an AI almost. It's a little bit confusing. But it's easy to follow though. I'm understanding exactly what he's saying, but the way he kind of writes his English is a little bit funky. At least I just use a lot of slang. Although we may have unrealistic short-term expectations for AI, the long-term picture is looking bright. We're only getting started in applying deep learning to many important problems for which it could prove transformative, from medical diagnoses to digital assistants. In 2017, in this very book I wrote, right now it may seem hard to believe that AI could have a large impact on our world because it isn't yet widely deployed. Much as back in 1995, it would have been difficult to believe in the future impact of the internet. Back then, most people didn't see how the internet was relevant to them and how it was going to change their lives. The same is true for deep learning and AI today. But make no mistake, AI is coming. In a not so distant future, AI will be your assistant, even your friend. It will answer your questions, help educate your kids, and watch over your health. It will deliver your groceries to your door and drive you from point A to point B. It will be your interface to an increasingly complex and information intensive world. And even more important, AI will help humanity as a whole move forward by assisting human scientists in a new breakthrough discoveries across all scientific fields from genomics to mathematics. Crazy claim. Fast forward to 2025, most of these things have either come true or are on the verge of coming true, and this is just the beginning. Tens of millions of people are using AI chatbots like GPT, Gemini, and Claude as assistants on a daily basis. In fact, question answering and educating your kids' homework assistants have turned out to be the top applications of these chatbots. For many people, AI is already the go-to interface to the world's information. Hundreds of thousands of people interact with AI friends in applications such as Chatter.ai. Fully autonomous driving is already deployed at scale in large major cities. AI is making major strides towards helping accelerate science. The AlphaFold model from DeepMind is helping biologists predict protein structures with unprecedented accuracy. Renowned mathematician Terence Tao believes that by around 2026, AI could become a reliable co-author in mathematical research and other fields when used appropriately. The AI revolution, once a distant vision, is now rapidly unfolding before our eyes. On the way, we may face a few setbacks, in much the same way the internet industry was overhyped in the 1998 to 1999 and suffered from a crash that dried up investment throughout the early 2000s, but we'll get there eventually. AI will end up being applied to nearly every process that makes up our society and our daily lives, much like the internet is today. Don't believe the short-term hype, but do believe the long-term vision. It may take a while for AI to be deployed to its true potential, a potential the full extent of which no one yet has dared to dream, but AI is coming and it will transform our world in a fantastic way. Wow. That was a pretty that was on it like a like it's a very like eye opening. I have a hard time putting together the words for how to describe like 'cause I was I was 1 years old. I was born in '99. I was 1 years old when the internet came out, right, and started becoming like fully adopted into things, right. So like I just don't know. And but the internet, that was such a huge change, right. Like at what scale is this different? This is like it's in line with that change, but is it as grand? Yeah, maybe. But the internet was like, you think about like everything that it unlocked from being completely nothing, like just like word mouth to just everything being digitized over the course of a couple of years because of the internet, right? And things like that. So it's just at what scale could we see these effects? And like it's saying like, these renowned researchers and people writing these books, right? If you invested in internet companies like Google and whatnot, a lot of them went under, right? But the larger ones that were, had a lot of the backing, those ones stayed around, and the investments exponentially grew, right? So there's a lot of short-term hype now, but in 10 years, are we going to see a similar kind of investment explosion that we see with like Google from 99 to what we see Google at 2017 to 2025, right? I mean, we already are seeing some stuff. It's really interesting. I was just talking about the hype of the industry when it was adopted here in the 90s and 2000s. Not when it was like first developed back in, at the schools or whatever. Just relevant to this section here. But yeah, it's just interesting, right? But I'm really excited to keep going with the book. This author seems pretty it seems pretty good about giving us good understanding about things that what's going on, and hopefully it made a claim that by the end of this book we should be able to come up and write our own stuff. So I'm really looking forward to being able to unlock those skills if I was you know if we're able to unlock those skills at the end of this book, right. We'll see if it comes true, because it makes a pretty bold claim there, right. um all right, you guys, let me do a little sign off for the YouTube here. and then I'll go ahead and head out for tonight too. All right. Thanks so much for being here, you guys. This was chapter 1 of Deep Learning with Python. What is deep learning? Thanks so much for being here. I'll post my notes in a GitHub repo you can find in the description down below, as well as in my Discord. I'll put the link to the book, and I'll create a section. So thanks so much for being here, and I'll see you guys in chapter 2. Okay, I'll go ahead and stop the recording there. Nice. Any chats here? If you read this whole book and understand it, you'll be on most CS undergrads who are finished. That's honestly that's a good, I want to do it. I want to challenge ourselves. I want to push through. I want to understand it. We're one chapter down out of 20. I feel good about the material we just read. Yes, this wasn't very, technical. This was a lot of just background, but um, I really think that if we just go at our own pace, I think that that's the difference between college, like school, and self-learning. If you have discipline, is that with college you're forced to move on subjects before you're maybe ready to move on, and as you compound, yeah, you might fill those gaps as you compound, but some people, as you compound, those gaps just get bigger and bigger and bigger, and then they can't keep up, and they're just struggling, and then they result to cheating and stuff. So I think the difference that we're able to do this independently is that we can sit here for an hour and 56 minutes and read the entire chapter, taking detailed notes, and make sure that we understood every definition. We understood like what he was talking about. We don't need to move on prematurely. And I know it might seem like, oh, like a rush to get the course done, right? Like I tried to not think of it that way. Like, oh, if I just get this course done, I'll have this skill. Well, that's kind of thinking about college in the way that is screwing a lot of people right now. Is, oh, if I just get this degree, I automatically am entitled to some job. That's no longer the case anymore. Is that the degree gives you skills, and if you don't learn those skills and practice those skills while you're getting the degree to where then you can translate them into real world employment, then it's not gonna work out, right? You can you can I really think that that holds true, and and it's all, everybody has their own ideas and stuff, but and what do you guys think about it? It's kind of an interesting topic to think about, um, and whatnot. Yeah, this book is Deep Learning with Python. It's just right up here, my guy. I'll post a link to it in my Discord after the stream here. I'll make a section for it. But yeah, I often felt like a lot of my peers in college, like if they were struggling with the material and they were forced to move on, they were just gonna have to like, okay, I just have to keep going. Like, I just have to, I have to move on. I have a test in 2 weeks, like, or I took the test, I failed it. I don't have time to review the test because I have another test in 2 weeks and I have class tomorrow going over new material. Like, it's just like, oh, it just feels like you can drown. And so I really think that that's where college has it wrong. And so it is, and I'll kind of touch back on the thing of, really, if you guys are in college, I'll try to give maybe a little bit of advice, and take this with a grain of salt because I'm not in school anymore, but this is someone coming out of college at the end of COVID, when things were kind of falling, and I was still able to get employment at the end there. And um, I want to say, like, you really need to try your best to, if you're forced to move on, you've got to try to fill those gaps by doing extra effort, getting extra assistance. You have a lot of resources at college that you're paying thousands of dollars for. Use them. Like, be annoying to your professors, be annoying to your TAs. Like, you're paying thousands of dollars for yourself and investing in yourself. You know, you need to advocate for yourself and be annoying, and be persistent and get the help you need. And if you're not understanding it, just keep grilling them, and I need help, I need help, I need help, I need you to, like, that's their job. And yeah, then some of those professors, they might kick back on you and be like, oh, blah 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 blah, and yeah, you need to put in a little bit of work yourself, and whatnot, and be able to try, right? You have to be an adult, but at the end of the day, that's their job, is to help you and to teach you. And so use those resources appropriately. Don't, be shameless. Just like, who cares? Like, you're only there for 4 years. So just like, and honestly, the people, I haven't talked to probably like 99% of the people I met in college. So if I was annoying, who really cares? Because I have a job now. I'm not, who cares where, I don't know where they are. Like, who knows? Like, it doesn't matter. It really does not matter at the end of the day. Um, so advocate for yourself, get those resources that you have available to you, and fill the gaps. Don't move on prematurely if you aren't ready to move on from the. I think that's what's been having us be successful in learning programming and being able to build projects and implement our learning is because I'm not moving on until I understand what I learned. Like when we learned classes in object oriented programming in Python, that was really hard at first. Like I had no idea what was going on because we were still trying to learn Python and still trying to pick up the slack and stuff. But I stuck with it. I just stuck like 2 weeks. We just stuck on classes, doing example after example after example, thinking it through with real world examples, like off stream, like in the shower, just thinking about it, you know. So, kind of consume yourself with the material. You're there for 4 years, so just consume yourself, buy in. You're already paying for it. You're literally buying in with your physical money, so buy in mentally. And if you're in college, that's the one thing I can tell to give you guys, because a lot of people, they treat college as this entitlement to where, oh, I was accepted into college. I have this I'm going to get this degree if I just follow this process, and I have all the, I can kind of get by with C's or D's and still get this degree, so it's kind of okay, it's whatever. But then I come out of college, and you think that this is like a golden ticket to a job. Well, it really just in today's right now, a college degree is honestly never meant less, right? So you have to have more to yourself. Like you have to be able to not the skills in the degree. Um, like I don't know, it's hard because honestly, I don't remember a ton from like the niche skills in chemistry, and I didn't really use a lot of those niche skills in the lab. Um, but it mainly was more like basic laboratory skills and being able to like critically think, adapt to business scenarios. Um, I think having a good understanding of business is also helpful. It makes like when certain business cuts and decisions happen, it makes sure you can understand why they're happening and they don't hurt as much. Um, Things like that. I don't know. Anyways, that's enough of my ramble. I'm sorry. I don't know if you guys have any opinions from current CS majors or people in college. What do you guys think? Hey, Jimmy Boats. Also, you're covering the basics from the ground up. I agree. College moves too quick from the basics. Plus, a class like deep learning would be 11 weeks trying to cover a massive section of the field. Yeah. You think you'll be able to fall in a quant job? I don't know. I know I do have some financial education and ability. I do trade and I've been able to be successful in the market somewhat. So, but I don't know. I have the benefit that I've been a self-taught engineer for years already. So going into this already has a massive background in the field. Yeah, there. Let me tell you guys this one story. I was in a I think I was in my advanced biology 2 course in college. Um, I think that this course you were learning about things, like the Krebs cycle and citric acid cycle, like the electron transport trains, like these different types of biochemical process chains inside the body that convert ATP into like energy and fuel and stuff like that, or convert stuff into ATP and whatever. So but I vividly remember this. I was sitting in a lecture hall, and there it was probably about 3/4 filled. It's a pretty large hall. Um, but there was this guy up front. He maybe was a few years older than me. I think we were in the same grade. I think he just started a little bit later in college. Maybe he was a year older and maybe a grade older. Um, but let me tell you, like he sat there with the professor while she was going over these deep kind of biochemical inner workings, and he was having like a fluent conversation with her um, about the material, and I was just kind of sitting there, just kind of like stunned, like just being kind of like, what's going on? You're like, how is this? How is he so? And it stuck with me to this day, right? And I've always just kind of thought like I wanted to be like that guy, right? Like, and I bet you he probably just read the chapter beforehand. He probably took his time and cared and bought into the material more than I did at the time. I was focused on, other college things, and not, it wasn't as focused at school or whatever. It just, he was just, I don't know. He just seemed like he was cracked. He just knew what he was talking about, and he knew it in his heart. He knew how these things worked, what these chains did, where these certain, you know, um, units went in the body, and like it was really impressive. So, anyways, I'll just leave it with that little anecdote with you guys, um, and be like that guy. Come to class, already knowing the material, so that when you're learning, it's just review, and it's just like solidifying the review. Like it's I don't know. What do you guys think? Yeah, tutoring labs, right? I was in my physics tutoring lab probably 2 or 3 times a week. When I was in physics class, I also, when I was in calculus, I was in the mathematics tutoring lab. I think 2 or 3 times a week during that summer when I took that course. Um, you got to use those resources. I honestly don't think it's the students' fault. A lot of the college is just too easy now. The grade inflation is crazy. That is interesting, right? You're I think colleges are faced with a lot of pressure right now to, especially with increasing unemployment rates for a lot of their key marketing majors, engineering, computer science, mathematics, physics, like these kind of key marketed majors for, STEM, their employment rates are going up. And so I feel like as a measure, they're passing students more, or they're also, wanting more funding. They're businesses, like they're nonprofit, but they're business minded, so they're wanting more funding and more acceptance, so they don't want to fail students out, because if students drop out or fail out, they have less money. They're not enrolling next semester, right? So if they just pass them barely, they're a guaranteed check next semester, right? So would we rather barely pass them or lose that 50,000 annually, right? Now stretch that across, let's say, 5,000 students. It's a good, like, you know, good chunk of change that you're missing if you're failing students like on the borderline. So I think that's where maybe that's coming from, Braden. Um, also, dude, I'm not gonna be that guy, but some college majors are pretty easy. Like, I'm not gonna say any examples. I'm not gonna offend anybody, but there's a significant difference in the course load requirements for a computer science or a biology major or a physics major, an engineering major, than it is to like a health and human services major, or like a public health, or like comms, or family services, or that was a popular one at my college. um, yeah, things like that. So I don't know. Interesting talks. I'm a CS grad, and the classes I learned the most from are the ones that the professor didn't shy away from hard material or pass people because they didn't deserve it. College also very good to build the who you know part of getting the job. That's also another thing that's going on right now, right? You guys, is it's honestly, you guys, the 100. I was thinking about making a video on it, like an actual, just like a straight up, just a video, just talking for like 5 minutes, maybe trying to provide some like advice, or maybe some just in the field, like what I'm seeing, like that I have a job in the STEM field. I can see kind of what's going on ish, like what I'm noticing. And I was gonna, like, a big topic in that is, if you see open positions online, I'd say 75% of the time or greater, it's posted for an internal person. And that's what I don't think people get, is the company is just posting the position already knowing who they're going to hire internally or promote internally, because they don't want to go through like a raise. They need them to apply so that they can absolve their previous position rather than backfilling it so they can, save on budget. Like, that's a lot of stuff I'm seeing right now, is like, okay, we're going to post a position rather than promoting you. You apply for it, so we have a vacancy. Now we can justify closing rather than just having you have moved into like a promotion, right? So like it's like a backfill that we can now delete, right? So it's like they're creatively trying to find ways to reduce their budget by eliminating, like, yeah, they legally have to postage, right? So, you know, if you're going in blind, you guys, like, just know that your efforts, it might be like a sunk cost, like trying to like just keep firing blinds. Like, I fire blinds like all the time, right? And the only success I got being in industry of biology and biochem was an internal transfer. Like, it's just, I fell victim to that because that's the only options that I was getting, because I'm sure that's the only options a lot of other people are getting as well. Like, they, if it's happening to me, it's probably happening to other people. Like, we're just shuffling around between teams, job to job, as they eliminate positions, as they sell off certain portions of the businesses, as they, as things get outsourced. You know, it's really interesting. I know we have a lot of like H1B viewers, and a lot of like Indian viewers, and a lot of foreign viewers. So I'm not going to comment on any of that at all, because I just don't want to ruffle feathers or anything like that. I know there's a lot of opinions along American employment and things like that. But yeah. Anyways, yeah, I have a job I work in a biology lab. I worked as a chemist, and now I work as like a lab manager. Uh, Admin thing. All right, you guys, thanks so much for being here and hanging out with me today. I'll go ahead and chop up this recording that I did of the reading of Deep Learning in Python. I'll go ahead and post this book in my Discord link down below. And thanks so much for being here. We'll continue on with Chapter 2, probably either not tomorrow or the day after. I'm going to probably alternate days of this and C. I still want to keep going with our C programming. I'm really enjoying that. But thank you guys so much for being here. I'll see you guys tomorrow. Peace out.